Bismillah ar-Rahman ar-Rahim. Good afternoon, everyone. Our lecture today will explain the electric field inside the depletion region in p-n junction. An electric field is created like this diagram shows to us in the depletion region by the separation of the positive charge and minus charge, negative charge densities. Let me put this here. That will be appropriate. Yes, let's keep going. Here, this figure 7.4, the space charge density in a uniformly doped p-n junction. Here we'll assume the abrupt junction approximation. Now, this is important. We must know here we will assume that the space charge region abruptly ends in the n region at x equal plus xn, and in p region when x will equal minus xp. And we know actually sp is positively quantity. And after that, we will do a simple review to depletion region or space charge region. It is a region in both sides of a meteorological junction in which there is no free carriers present. And we explained the reason of that, just ionized impurities inside it. The total charge in n side, in n region, is Q plus electron donor concentration width in depletion region to n side dot area here, not actually area, but we can say it is a cross-sectional area of the sample, a cross-sectional area of the sample. This equation will be important to us because we will depend on it and put this result in another equation to can calculate the last result to energy field at the depletion region in p-n junction. Now, let's talk about the total charge in p side. In p side, we'll put minus beside the Q to can calculate the potential here, but in p side, equal minus electron charge, acceptor concentration dot width in depletion region to p side dot sectional area, like I said here, this diagram 7.4 here in n side x will equal plus xn, in p side x will be different, equal minus xp, and like we said before, xp actually is positively charged, positively quantity. And here we have two limits, minus electron acceptor concentration and up plus electron donor concentration. And here this line showed to us the volume charge and his unit column divided on centimeters to force 3. Let's keep going. Like we said before, A equal a cross-sectional area. Here, the total charge in n side will equal the total charge in p side. That means the absolute value to potential at the n side equal the absolute value to potential at the p side. Here, at neutrality condition, that means just we will put the results of the last equations here. The potential at the n side equal electron donor concentration width in depletion region at n side, and here across sectional area. Yes, that's right. equal minus electron acceptor concentration width of inside the depletion region at the p side cross-sectional area. Now the electric field is determined from Poisson's equation. Here we totally will depend on Poisson's equation to can calculate the electric field at the inside the depletion region to p-n junction. And this will be the most important equation to us, as its number is 7.11. We will use it at this lecture maybe 2 or 3 times. Like I said before, it is the electric potential, it is the electric field, and here it is the volume charge. It's important here, it's a different element. It is the permittivity of the semiconductor. Now let's work at first with inside. We have 2 different volume charge to each of n-side and p-side. Like I said before, we will start from n-side. Here the volume charge equal E electron charge dot donor concentration. His unit will be Coulomb divided on actually centimeter to force 3 or meter to force 3, I'm not sure. This limit here will be x bigger than 0, smaller than width in the depletion region to n type. This will be 7.12a, and in p side will be 7.12b. Here the volume charge will be different. Just we will put acceptor concentration instead donor concentration to be this volume charge belong to p side. Here the electric field in p region found by integration to equation 7.11. That's me what we will do. Now we want to calculate the result of the electric field, but in p region we will use the equation 7.11 here to do some relationship between, we will benefit from the relationship between these 2 elements. We will ignore the differentiation of square of the potential, and just we will dealing with these 2 elements with the volume minus volume charge divided on the permittivity of the semiconductor equal minus derivation sub x to electric field. Yes. Let's keep going. Here, like we know, E sub x equal integration derivation sub x to energy field equal minus volume charge divided on permittivity of the semiconductor. That's mean here E equal minus volume charge divided on permittivity of the semiconductor dot dx. After that, just we will put the result of volume charge at the p side. After that, calculate this equation again. That's mean minus integration E acceptor concentration divided on permittivity dot dx. Here, the equation 7.13 will be electric field here, the energy electric here, and p region equal minus E acceptor concentration divided on permittivity dot x, but plus the integration constant, because I have another more than one integration constant, because that here I'm use number 1, and after that I will use number 2, something like that. Let's ignore it. There's 7.13. Like I said before, C1, it is a constant of integration. The electric field is assumed to be 0. I will use another math trick to calculate the constant, the integration constant, and after that I will put this result in equation 7.13 to simplify the electric field equation more and more. Okay, let's keep going here. The electric field, to find the result of the integration constant, we will dealing with electric field here will be 0, and the natural P region for X will be smaller than minus width in the P region, since the currents are 0 in thermal equilibrium. That's important when we're dealing with natural region. That's mean here the electric field will equal 0. Since there are no surface charge densities within the p-n junction structure, the electric field is a continuous function. It's important when the electron is a continuous function, since when we don't dealing with surface, don't has any densities within p-n junction structure. Here, the electric field in the P region is determined by sitting, like I said before, with natural region. That's mean electric field equals 0. And here at the P type, X equal minus XP, like the figure in 7.4 or 5. I can't remember here, 7.4. Here, X will equal at P region minus XP, and here X at N region will equal plus XN width in N region. Let's keep going. Here, 0 equal minus electron acceptor concentration divided on permittivity dot minus width at P region plus the integration constant. After that, the integration constant equal minus E acceptor concentration divided on permittivity dot width in P region. We will put this result to see number 1 here to can modify the equation, or we can say to calculate the result of the electric field inside the depletion region. Because that here, the electric field and the depletion region at P region or P side equal minus E acceptor concentration divided on permittivity X plus XP, when X bigger than or small minus XP or smaller than or equal 0. Like I wrote here, we're dealing with the two common factors, similar common factors, because that I put it here outside the bracket and just left inside the bracket X minus XP. And dealing with the minus, I put it outside. After that, put plus between X and XP. This equation is 7.40 will be. Now let's start to calculate the electric field, but in N region together, found by integration the equation 7.11. Like I said before, today this equation will be the most important equation to us because we will using it too much. But here, the idea we will use the same idea, the same equation, but here, like we know, volume charge has another equation, another result, and N type, and N side equal electron donor concentration when X bigger than 0, small than width in N region. Just we will put this results here and derivative all that by and put integration to can take just the electric field equal what? Here equal minus integration volume charge divided on permittivity dot dx. After that, put this result here, E donor concentration, to find the result about the equation about the electric field inside the depletion region and side with the integration constant number 2. Now, the same idea, we used it before. We will try to calculate C2 to can modify this equation more. To calculate the result of C2 in natural region. What does mean natural region? That's mean here the electric field will equal 0 when X at P side equal Xn, like in diagram number 7.4. Where is the diagram? X equal plus Xn at N side. The same idea. Let's start to modify this equation. We will put here 0. We will put here X sub N. And after that, the C2 will equal E donor concentration divided on permittivity dot width and side. Let's put this result here to can modify the result of the electric field in the depletion region. Here, the electric field and the depletion region at N side equal electron donor concentration divided on permittivity dot width and N type minus X, when X bigger than or small 0, smaller than or equal width and N side. This equation will be 7.16. Now, let's start to, here the electric field is also continuous at the metallurgical junction, or when X equals 0. My wife sent message. Yeah. Let's continue. Here, what that's mean? When X equals 0, that's mean here the electric field at N region equal the electric field at P region, but at under one condition, must X equal 0. If X not equal 0, don't equal 0, no way. En will not equal EP. Here, let's put the results of the electric field in N type and electric field in P type. And after that, modified all of that. Now, just we will put 0 instead of X and calculate all of that again. But here, I'm wondering, because this positive, the right equation, the right charge to this equation is a plus, positive. I put positive here, and this from equation number 7.16, and this equation similar, the same equation. I take this equation from the source with the same number, but here, if I don't put negative here, I can't take or write the same equation 7.17 with the source, because that we must put here minus. But why, I don't know actually, honestly. If anyone can answer me, I will be thank you. Let's keep going. Here, plus END divided on permittivity, width in N region minus X, and we will write the result of electric field on P side equal minus E acceptor concentration divided on permittivity between two brackets X plus width in P region. Let's put x instead of x here, we'll put 0 and calculate all of that again. We will have donor concentration dot width in N region equal acceptor concentration dot width in P region. This will be equation 7.17. No way to write this equation if x not equal 0. The 7.17 equation means the negative charge per unit area in the P region, like here, in the P region, the negative charge in P region equal the number of positive charge at N region. Here we have another diagram, this diagram 7.5, explain to us the electric field in the space charge region of a uniformly doped p-n junction. Like I said before, we're dealing with uniformly doped p-n junction. Here, the width in N side, the width in P side, but here we wrote minus. Here, the electric field, the electric direction of from N type to P type. Here is a plot of the electric field in the depletion region. The electric here is direction from, like I said before, from N to P region, or in the minus X direction for the geometry. Here, the electric field is a linear function. This is important, we must note that, of distance through the junction. A linear function through the junction, okay? At the maximum magnitude, electric field occurs at the metallurgical junction. Here, an E exists in the depletion region, even when no voltage is applied between P and N region. There's something like condition. We must dealing with no voltage is applied between P and N region to can dealing with electric field exist inside the depletion region. Here, the potential in the junction is found by integration the electric field. Now we will start. Now we know all the results to the electric field at the P region and N region. And like I said before, we're dealing with the most important equation, 7.11, but with these two elements. Why? To can calculate, to can determine the result of electric field inside the depletion region. But now here we will start to calculate the potential results in this lecture, in this second. In this lecture, we will start using the same equation, but to calculate another element. This element will be the potential in the junction, okay? We will take these two elements at the right and at the left, derivation x, derivation 2 sub x to potential equal derivation sub x to electric field. By using a simple simple math trick, Ax equal minus the derivation sub x to the potential. This will be important to us because we will use it, because this equation explains, shows to us the relation between the electric field and the potential. To find the potential, this element, in this junction, we will take the integration of E to can find the equation, to can calculate the equation of the potential. By this way, here the potential will equal minus integration electric field dot dx. This equation will be 7.80. Let's go to another slide. Here we will solve this equation separately in N side alone and in P side separated by replacing respective solution of Ax. Let's start with another important thing. Now let's try to calculate together the potential, but in P side at first of the junction. Like I said before, we will start with at the P side and at the N side with the same equation. This equation will be 7.18. The potential equal minus integration electric field dot dx. Like we know, at the P side, that's mean here, EP, electric field at P region. Because that, we know the result of the electric field at the P region, we will put this result instead of electric field and calculate all these elements again. Like we're seeing here, we will take all this element and put it out. The integration will be integration x plus width at P region dot dx. Let's do that alone, and after that, put this result in this equation again, equal x to force 2 divided on 2 plus xp width at P region plus C1 dash. I put it, this dash, I mean, to know to can differ between the others because I use the same letter here, because that I put it this dash. C1 dash, this will be the constant integration to this process. Here, the equation of the potential at the P side equal electron don't acceptor concentration divided on permittivity between two brackets, x to force 2 divided on 2 plus x width in P region plus the integration constant. Now we must find the integration constant to come put this result here to come modify equation 7.19. Like I said before, to can calculate C1 dash, we will assume we're dealing with potential equal 0, and x at P side will equal minus x P width at P region, like the diagram 7.4. Just we will put these two results in the 7.19 equation and try to calculate all that again to come find the result of the constant integration constant. Like we're seeing here, C1 dash equal minus electron acceptor concentration derivative minus 1 divided on 2 width at P region square. After that, let's modify it. We can delete these two minus because minus dot minus equal positive here, and equation 7.20 will equal electron acceptor concentration divided on 2 permittivity dot width at P region square. Just we will put 7.20 at the result of the potential at the P side at 7.19 to can calculate the last result of the potential at the P region. Here, like we are seeing here, equation 7.21 will equal electron acceptor concentration divided on 2 permittivity x plus width at P type, all that square, when x bigger than at P region, bigger than or small minus width at P region, and smaller than or equal 0. Now let's start to calculate the potential by using the same idea, but we were dealing with N type. Let's start to calculate the potential on this region. We will using the same equation, like I said before, 7.18, and we know En sub x equal what? Equal E acceptor concentration divided on permittivity between two brackets width in N region minus x, when x bigger than or small 0, smaller than or equal x width in N region. Just we will put this equation here and calc integration, take the integration to all that. Here, we can take the integration to this side alone, and the last result will be x squared divided on 2 minus width in N region dot x plus the integration constant number 2. After that, we will put this result instead of the integration and write the potential equation in N region again. Equal minus E donor concentration divided on permittivity between two brackets, x squared divided on 2 minus width in N region dot x plus integration constant number 2. This will be equation 7.23. Now let's use the same idea to calculate the result of C2 dash. We will dealing with potential in N region equal 0 and x equal x plus xn, and calculate all that again to come find this result. Here, after all that, we dealing with integration constant number 2 equal half electron donor concentration divided on permittivity width in N region squared. But we will use another idea here to come find C2 dash. When x equals 0, what does mean? Like the same idea when was dealing with calculation with compression between E in N region and E in P region at the x equals 0. The both of them were equal the same result. Now we apply the same idea, but not with the energy field, with the potential at N region and P region. When x equals 0, both of them will have the same result, because that let's start from potential at P region at x equals 0. We know the result of equation 7.21. Sorry, have electron acceptor concentration divided on permittivity between two brackets x plus width at P region, all of that square. Now let's put x instead of x here 0 and calculate the last equation. That will be have electron acceptor concentration divided on permittivity dot width at P region square. That's mean the potential at N region at x equals 0 equal the same equation, the same elements. But here we know the equation 7.23. Let's dealing with it, and after that we will come back to solve this idea. Here, the potential to the N region to x equal the minus electron donor concentration divided on permittivity between two brackets x squared divided on 2 minus width in N region x plus the integration constant number 2. Now, if we dealing with x equals 0, just we will put 0 instead of any x here. Here, like we know, any elements dot 0 equals 0, because that here the remain element will be the integration constant. That's mean the potential at N type when x equals 0 equal just the remaining element, and this remaining element is the integration constant dash number 2. Now that's mean here from this equation, when potential at p type when x equals 0 equal potential at n type n side when x equals 0. What does mean here? Here that's mean C integration constant number 2 equal have electron acceptor concentration divided on permittivity dot width in p side square. That's right. 724. Put in the equation 7.23 to can calculate, to can find the last result of the potential at n type, n side, the same meaning. Now, E and A divided on E permittivity dot xp square, we put it here, and this will be equation 7.25 when x bigger than or small 0, smaller than or equal xn. Now we found 4 elements: electric field at n region, electric field at p region, potential at n region, potential at p region. Now let's start to calculate and find the bolt potential barrier, like the last lecture, VBI. The magnitude of the potential at x equal xn equal belt barrier potential. Now that means we have dealing with condition. When x equal xn, x sub n, that means we dealing with same result of bolt barrier potential. When potential at n region sub x equal xn equal bolt barrier potential. What does mean? Let's put the original equation here, and after that put xn instead x. Here, like 7.25 E donor concentration divided on permittivity between two brackets width in n type x minus x square divided on 2 plus E acceptor concentration divided on 2 permittivity dot width in p region square. Now let's apply x equal xn and calculate what the result of belt barrier potential will be. Will be here after modify all of that and take the common factors outside and put the other between the brackets. VBI will equal E divided on 2 permittivity between two brackets donor concentration dot width in n type square plus acceptor concentration width in p region square, and this equation will be 7.26. Yes, but actually maybe I forget it right here. EVBI at last equal equation 7.26 equal VBI. Okay. Here, although we did this important note, I take it from the source. Like I said before, I depended on the same source. We still explaining all this information from chapter 7, the p-n junction, and it's the very important topic because the solar cell course and conductive course share the same topics, some topics, and the p-n junction, it's one of these topics. Although we didn't explicitly know the shape of the curve at the time. The right curve, we couldn't know it at our time, at this time. That's it. Our lecture is done. Thank you about your listening, your attention. Görüşürüz arkadaşlar. Kendinize bakın. Gelecekte derse görüşürüz. Eyvallah.